Our first talk in this session is entitled Lessons Learned, FPGA Prototyping of a Processor-Based Embedded Vision Application. The speaker is Markus Wloka, who is R&D Director for System-Level Solutions at Synopsys. He's responsible for the Processor Designer, System Studio, and SPW products. Markus is currently working on development tools for application-specific processors known as ASIPs that are used in embedded vision, imaging, LTE baseband, and other application domains. He received his PhD in computer science from Brown University in 1991. From 91 to 96, he worked for Motorola SPS in Tempe, Arizona, developing parallel processing software for low power characterization of ASIC standard cell libraries. He's co-inventor of 5 US patents and co-author of a general textbook on C and C++ debugging called The Developer's Guide to Debugging. Thank you, Markus.
Thank you. All right, so my name is Markus Wloka. I work out of Aachen in Germany, and I'll start with a brief introduction to my company. We are the leader in electronic design automation. We have, as of 2012, $1.76 billion in revenue, over 8,000 employees, and 90 offices worldwide, meaning we are very close to our customers wherever they are. Products that are relevant for the embedded vision community are, of course, the synthesis and verification tools that we have for system on chips and FPGAs. We are a leader for hardware IP. We offer solutions for USB, HDMI. We offer the ARC processor, not here, actually a large library of memories, as well as analog to digital converters. We also have an FPGA-based prototyping system called HAPS, as well as an emulation solution. And here what I will talk about is we have a tool for application-specific processor design. So, scope of my talk is we believe that embedded vision needs programmability. This is because the algorithms are complex. They are written in OpenCV or derived code, and it's not just a few lines that you need to put on the hardware. It's becoming large and staged libraries of software. Then we've actually been inspired through some other talks here and at previous summits where it was made clear that it's not like an FFT algorithm where you know what you're doing and also you know when you're done. You may have to drive the algorithm around and then change it in the field. So, as this is an emerging field, you need some stretch in your architectures. You may have to build a smaller or bigger device, and that will require software changes. The devices often need to be field programmable to tune the software, to train it, and then the inevitable updates all have to be uploaded. And then as we sell a solution to customers that will build embedded vision solutions, the solution has to be demonstrated. And we found out, what we're just showing here, it's with a white paper, we don't get quite the attention than with something that you can wave at and that we can actually change quickly to sort of get the requirements of the audience in. By following the literature, it's well known that for a lot of cases, the general purpose CPU and GPU is too inefficient, meaning it's either too slow, it eats too much power, or the footprint is too large. And that with application-specific processors called ASIPs, or I think in the previous talk in the other track, ICEs, you can get speed-ups going from 10 to 100 to 1,000 times, or you get a power reduction on the same order of magnitude. The FPGA prototype is a must. For the marketing guy on the team, he needs to show a portable demo. not just something running on a laptop, because we hope that our customers sell their solution. The algorithm designer needs to validate the solution, and as I'll go into, emulation solutions may be too slow. Running a frame-based algorithm on an RTL simulator is not possible today. Otherwise, some of the FPGA prototyping would actually be unnecessary. So it's in a lot of cases, we have good ISSs, instruction set simulators, virtual solutions, but for the graphics, video, and vision algorithms, you need raw performance, and so you need the FPGA. And then also, when you put the hardware and software together, turns out that some final checks can only be done with a real implementation. And most of our customers go to an FPGA prototype before they burn an ASIC, because if you make a mistake with an ASIC, that's going to be very expensive these days. Here's some examples of other companies developing processors that are programmable for embedded vision. Tensilica, ST Ericsson, Freescale, Siva, Toshiba, Analog Devices. Some of the solutions you can see here, they all believe that you need raw processing hardware combined with programmability. And so I'll actually not talk about our products, only indirectly. I'll talk about our flow and what went wrong and what we learned from it. And so here's how we thought it would work. So get the reference algorithm to work. OpenCV is great. We have a RISC processor with a matching compiler. And so with some small modifications, we were able to go compile and run the algorithm. This was Kenny Edge. And first booted this up on a simulator of the processor. So we had the live application. Actually, I think now we can do this in a matter of days. So you have something that you can demo, albeit it's going to be incredibly slow. But at least you can go try to find some software bugs. Sorry about that. So then, obviously we can generate out of our tool a processor simulator, and we can connect a debug server to the simulation, and we'll use the same server to the FPGA. We connect the debug server to the FPGA system later on. Straightforward technology, proven, should not have brought us any problems. Okay, now the fun starts, and this is the heroic stuff. We're doing supercomputer design by optimizing the vision algorithm and the coprocessor that goes into the hardware. This is a work where you do spreadsheet based optimizations on, do you have the memory bandwidth? Will you have the actual memory bandwidth through the pins of an FPGA? Build custom operations, and then, of course, following the book by Hennessy and Patterson, the dogma is if you build something custom with instructions, you need to have the memory path to it, otherwise forget about the performance. So this is the cool stuff. I needed a couple of tries to get that running by completely changing the Kenny Edge code, but reasonable amount of work. And then usually there is some fixed point data types that you need to induce because you don't want floating point hardware on there. And in the end, actually, I believe most of the design effort in the future will be the memory access of the algorithm. That's where the smarts are in every one of our customers' applications. And then you go and you debug and benchmark the software because we have the system. All right, going down the flow, generate the RTL hardware, and we go to the prototype and see the image, and you can see that, well, I'm sort of doing short shrift here. This is routine, right? And it wasn't. And so just to reiterate the performance, to get the performance, this is easy because we could measure on the simulator. We did some iterative operations. I'm just going through this here really quick. We put in bigger registers, some custom ops. Hello. And we're also not overdoing on the processor design. We're not touching the superscalar architectures. We certainly don't want to do out-of-order processing, and it's a 6-stage pipeline out of the book, really. And we also are not looking for the revolution in software development. We're using C++, really C with intrinsics, because we removed all the C++ code with the dynamic memory management. Okay, so the tuning worked. And then we got under stress. So we committed together with marketing to show a demo at the Mobile World Congress. Did a very aggressive deadline, and sort of also being overconfident, really underestimated now the work that was coming to get to a prototype. Okay, so we opened the catalog and bought some pieces. And so you can get good prototyping FPGA boards. I'm saying good, this is amazing hardware. You can put huge designs on these FPGA these days. And this is available from Xilinx, Altera, and also from Synopsys. Now, synthesis flows are mature. Obviously, at Synopsys, we have two good solutions with Design Compiler and Simplify Pro. This works. RTL simulation also is technology that's now decades old and is very mature also. This works, and this is where you find most of the logic errors that you didn't catch during the C-based system development. Hello? All right, so the first lesson is here. This is Check the Plug. This is from a book on debugging by Dave Aggans. And you've probably also done phone support with friends. And the first question that you ask when the computer is broken is, well, is it actually plugged in? And 30% success rate. So plug and play does not exist for FPGA prototyping. I have vacuum tube stereo equipment that's more plug and play than this. This is 0% plug and play. Now, as a Windows user, you can walk on the street. If you find a graphics card in a garage sale, plug it in. Microsoft makes a huge amount of money by recognizing any piece of hardware and getting it to run. All right, here, it turns out that not every card works in every socket, even if you can force it in. The voltages are incompatible. And each pin and each chip has to be individually configured. And there is no BIOS and no bring-up software to get a heartbeat out of these bricks. And so you need to develop a flow to get you to the stage where the system starts ticking. And then, while we have a great tool to generate a processor, there is also IP on the floor plan that you have to go and add. And so we needed to go find an AXI bus, SDRAMs, DVI, and then something to connect the debugger to. And again, none of it works out of the box. You desperately need to find a vendor with good examples, and then sort of hope that you can adjust the examples for your particular application, necessitating really a flow where you can go with an example from start to end, rather than being surprised somewhere in the middle for something that should be actually routine. And then, of course, don't just write the vision algorithm. You should write a test for every component you have there and try and isolate and first get it to work and then try to get coverage. Also, you need to read lots of documentation to see how you configure these components, and very good vendor support is key. So don't go for just the cheapest solution. Go find a partner, and we've had very good results with the people that we have worked with. It's out there, but you need to find them. And then you should debug often and early. We believe the advantage of our flow is that you develop your vision at a high level, and then you only go fix problems that come from refining the abstraction level. So, you go here, you get the software to run on the system simulator. It's called system simulator because it's one CPU. Should be a virtual platform if you have a multi-core system with more peripherals. And then at the RTL level, simulate, and you find all the logic bugs that somehow got introduced. And in the FPGA prototyping, hopefully you will only be debugging the difference to the logic level, which is configuration of components. And for that, to prove that this refinement can be done, you need to have lots of software tests, not just the algorithm under test. there to show that you have this consistency. All right. And then, you know, as the introduction said, I also co-wrote a book on debugging. Under stress, we threw everything away that we had in processes and know-how on how to debug, because our plan said we'll just load the image on the FPGA, then load the software, and we hope it runs. So we didn't write the test software that I was talking about. This came later. And so for our edge detection, this is actually a fake image. You see here that there is some interference pattern on it. The real image was me standing in front of the camera with a tweet code and a herringbone pattern, which made it even harder to identify the problem. And now something is wrong with the image. How do you find the error? So, okay. First question was, this is a 5-stage algorithm. At which stage of the algorithm does the error get introduced? And so we went to square one and rewrote the software to get at the individual stages of the code. And it turns out in the first stage, which is blurring, here there is a pixel wrong. So we laughed and said, so the person that wrote the code counted wrong in the array indexing. It's either the first or the last element where we miscounted. But no, the code actually turned out to be right, and it was right on the system simulator. So, and actually the wrong pixel is in the middle of a cell. So then next suspect is we got the bus wrong, so we thought it's a broken memory read. And so then we started writing test software for the memory components. No, that the memory worked. Okay, then cool error to have is a pipeline hazard where instructions interfere with each other. Can happen, but the advantage of having the software flow is that it was then relatively easy to insert no-ops into the instruction stream to rule out the pipeline hazards. Okay, no, that was not it. And then we asked the question, is it a critical path in synthesis? And indeed it was. And turned out we had actually read in an AXI part, and that removed some of the constraints for the synthesis. And essentially, we were running without timing constraints, which gave us the wrong design. Okay, we fixed that, and lo and behold, the image appeared. The lesson here is this was unnecessary. If we had written 10 times more software up front, our life would have been a lot less stressful, and we could have developed a lot faster. So, don't think about just algorithm development. You're thinking about a whole test system to validate the hardware here. And we're actually glad to have the programmability, because now imagine if this was a fixed RTL, which is also possible for a simple algorithm like that. If you want to get at the stages of the algorithm, it means resynthesis and a chance to also introduce new errors that are then harder to find than just making some quick software changes. All right, coming then to my conclusions, and I think we're doing okay with time. So we found that building an embedded vision system is actually a lot of fun. If we had called it beta test, my team would have been massively demotivated. But hey, we're building a real machine, and we're sort of seeing our success. So this is, and it's cool. You need to integrate many layers of technology. There is compiler generation, ISSs. There is processor design coming into play, and the whole mapping onto the FPGA. So there is some sophistication to this flow. It's very important to only go in small steps and keep your verification alive from step to step. Don't make too large bounds and abandon your test flow. Decompose the problem of a complicated vision algorithm into smaller parts and test these parts extensively. And then the final lesson is that thankfully, the second time around you'll do this, if you follow your proven architecture, it's going to be much easier, because these are problems that are not fundamental in nature. You solve them once, and then the components you have will stay on working. The compiler you have will stay on working. You'll be making small changes then in your refinement. All right, and with that, I conclude. Further resources are here on embeddedvision.com at the Synopsys websites. And please come visit our booth where we're giving a demo of now a working system. And we'll be glad to talk to you. Thank you.
So what questions do you all have for Markus? We shut off. First one to that.
Well, it seemed a little ironic that your example, the problem was with the synthesis tool that's the most mature tool. I'm wondering if you thought it was even possible to write test software to test something like that.
Well, synthesis tools usually have lots of complicated switches. And so they have improved over time to having standard flows. But since we were sort of integrating components that were untested by us, we didn't have a test bench for our bus. We just put it into the real design. Whereas I think somebody that's designing IP for a living would have a bus verification flow and would have caught that by slowly ramping up the clock speed and seeing where it was failing. So I mean, I take the blame instead of blaming it on the synthesis tool. We're not pushing the boundaries of synthesis here, by no means.
Next question. That's it.
That's it.
Okay.
Thank you very much.